Hi Algebra 2, welcome back to our second day of section 6.1. And you can see here we will continue to talk about exponential growth and decay, but we'll be focusing on modeling with exponential functions and interpreting and comparing exponential functions. As a warm-up though, I do want you to pause the video and write down the two transformations that you see for the graph of negative 4 to the x plus 1 compared to 4 to the x. Hopefully you were able to see that the negative in front would be a reflection, so it reflects over the x-axis. Okay, so that's a vertical flip. And then the plus 1 would shift it up 1. Now the reason I only asked you to describe the transformations is because we haven't really focused on the order of this. But if I was to graph this, so 4 to the x, remember my a is 1, so that's my y-intercept. Because there's no number there, it's like 1 times 4. I put a point there. Because 4, that's my b value is greater than 1, I know it's growth. So I could make a table, but in all reality, if I remember what I did yesterday, because that one hasn't shifted, it had a y or asymptote at y equals 0. Oops, I should have drawn that dotted. And this would have been the graph of just 4 to the x. Okay, so now here's the thing. When you have multiple shifts going on, you have to do the reflection first, which means first I would reflect that graph over the x-axis, so it becomes this. This is just negative 4 to the x. We talked about that yesterday a little bit. But now I shift it up 1. Okay, so I take the y-intercept that was at 0, I move it up, or negative 1, and I move it up to 0. I take the horizontal asymptote that was at 0, and I move it up to 1, and it actually would look like this. Okay, so again, that reflection does come first. You'll learn a lot more about that in pre-calculus. Okay, so those are understanding what the parent function looks like. Again, really being able to look at an exponential function and tell me the y-intercept, whether it's growth or decay. And then we described the key features. So the domain of my solid purple graph is still negative infinity to infinity. When it flipped over, it's a little bit different because it actually goes down to the negative. So it goes down to negative infinity forever. And remember, now it's approaching this asymptote, which is actually at 1 now. Okay, it has a y-intercept, we already said, at 0, 0 this time because it moved up to 0. And the end behavior as x approaches infinity, so this side, it actually goes down forever. So f of x goes to negative infinity. And then as we go the other way, as x goes to negative infinity, f of x approaches, that's where it's approaching this asymptote. So our end behavior always approaches an asymptote on one end, so that's a number. All right, so that's reviewing a little bit with what we did yesterday. Today we're going to be switching. We're going to actually be writing equations given situations. So when we write exponential growth and decay functions, a is the initial amount or the starting point that the problem is talking about. So you'll want to get this in your notes, okay? So pause the video, make sure you get these down. R is going to be the rate of increase or decrease. It's usually given as a percent. You need to convert it to a decimal. And AFT, so what you're solving for is the amount of time after t time period. So t is time. So t is time, AFT is kind of the final amount. All right, so we can see on the left-hand side here, we have growth, which is increasing. And this is where it comes back to what I kind of told you yesterday. So you're taking that initial amount A times 1 plus the growth rate as a decimal. So the reason we have to add 1 to it is anytime you take a percent and change it to a decimal, it's going to be between 0 and 1. What we talked about yesterday is if b is between 0 and 1, it's actually going to be decay. So you have to add that 1 to it. Okay, so the growth factor b is always 1 plus r. Okay, if it's a decay situation, so if whatever you're talking about is going down, the only thing that changes is you have to do 1 minus r inside. So your b value is always 1 minus the rate. A common mistake would be, again, just to put the r in as the percent, but that would tell you how much you get off versus how much it's actually worth. So there's a slight difference between the two. Okay, so let's look at an example. This says the population of a large city was about 4.6 million in the year 2010 and grew at a rate of 1.3% for the next 4 years. What exponential function models the population of the city over the 4-year period? Now, this is going to be my a value. 4.6 is the initial starting amount. If they're saying 2010 is the starting amount, that's actually the beginning year, okay? As soon as I see that it's growing, that's when I have to do the 1 plus r inside parentheses, and the rate is 1.3%. Now remember, you have to move that decimal place 2 times, so I'm going to put that in as 0.013. Okay, so when I go to write my exponential function, as we saw in the last one, we would do a of t, or you could do f of x, it doesn't matter, equals 4.6. Now we'll have to remember later that that's in millions, times 1 plus, because it's growth, this r that I converted to a decimal point, 0.013. If you have a t here, you have to put a t here. Okay, so you got to make sure you read Pearson carefully, because if they ask you to put it in terms of t and you put x's, they'll count it wrong. If they put f of x, you'd have to put an x as the exponent. So you just have to be careful and look at what they're doing there. Now, I do believe Pearson sometimes wants you to write it like this. There was once I typed in, I added it together and they counted it wrong for some reason. Otherwise, if they don't care, you could simplify. It's 4.6 times 1.013 to the t. Okay, so typically this is the function that I would work with. But again, I think there's one on your homework where Pearson makes you put the plus in between there. They want to see it all. All right, so once we have that, then we have to be able to use it to answer questions. It says, if the population continues to grow at the same rate, what will the population be in 2040? Now remember, we started in 2010, so we would have to take 2040 minus 2010, and I get 30. So we're actually going to figure out the answer when t equals 30. Okay, so in order to do that, I am going to go a of 30. Now we're just dealing with functions, 4.6 times 1.013 to the 30th power. I would type all that into my calculator in one shot, and I get about 6.78. So I did round, but don't forget, this was in millions, so we'd have to put 6.78 million. Otherwise, that answer doesn't make sense. Okay, so my answer is 6.78 million. So if we want to write it out as a sentence, in 2040, the population of the city will be about 6.78 million. Okay, and again, you don't usually have to type that out as a sentence in Pearson, but sometimes they give it to you as a sentence. And I'll show you later how you can make sure you know how to type this into your calculator. All right, so now I want you to try it. Okay, so this one, they actually end up giving you the function, so I just want you to try typing it into your calculator. Okay? All right, a factory purchased a 3D printer in 2010. The value of the printer is modeled by the function, and it gives me the function, where x is the number of years since 2010. What is the value of the printer after 10 years? Well, that's just asking me to do f of 10. So again, this is where you're checking to see if you're typing it incorrectly. You would use your caret key to the 10th power. Okay? And when I typed that in, I got 14.52. Okay, so about 14.52. So that's the value of the printer after 10 years. It's worth $14.52. Now this next question you might have got a little stumped on. It says, does the printer lose more of its value in the first 10 years or the second 10 years? Well, my loss in first 10 years, that's what 10 years. Okay, it started at $30. Its new value after 10 years was $14.52. That means it lost a total value of $15.45. Okay, so 15.48. Sorry, my writing. Okay, so in the first 10 years, it lost value of $15.48. In order to figure out the value it lost in the next 10 years, I would have to figure out the total amount 10 years later. So I already figured out after 10 years, so now I have to figure it out after 20 years. Okay, so I'd have to do 30 times 0.093 to the 20th. When I typed that into my calculator, I got $7.03 was the value of the printer after 20 years. Well, then I have to figure out, to answer this question, I have to figure out the loss in the second 10 years. So that's from 10 to 20 years. So I still subtract, but this time I'm going to take the 14.52 that it was worth after 10 years, subtract the 703 that it was worth after 20 years, and I only lost the value of $7.49. So it actually lost more value in the first 10 years. Okay, so that was the answer to that question. And again, the reason being is because when I did the subtraction, I got a bigger number up on top here. Having said that, again, the biggest skill you need to be able to do is understand, given these functions, you got to be able to type it into your calculator with the appropriate x values. Okay, now let's add a layer. Okay, so in this problem, it says interpret an exponential function. A car was purchased for $24,000. The function y equals 24 times 0.8 to the x can be used to model the value of the car in thousands of dollars x years after it was purchased. So again, it's giving me the function, but now they're going to ask me to figure out some things. First, it asks, does it, or it tells me, I guess, that it represents exponential decay and asks why. It could just say, which one is it? And the reason it's exponential decay is my b value is 0.8. Okay, so that number that's taken to the exponent, 0.8 is less than 1, so it's decay. Okay, so we learned anytime that the base, the b, is less than 1, that's when it's going to be decay. All right, so that's the first thing. Now it says, what is the rate of decay for this function? Well, we learned on the first slide today that b is 1 minus r, and r is the rate of decay. So we need to figure that out. Well, in this case, we know that b is 0.8. So I could just do my math. I get negative 0.2 equals negative r. Well, then I can just make both these positive. So r equals 0.2. Okay? Now, that's what the r is. But remember, usually they give me words in the problem that would help me find r. This time they're just giving me the equation. If they had written this out in the problem, an r of 2.2 would have been a percent, so it would have been 20%. And because my b is less than 1, it actually means that the car's value decreases 20% per year. Okay, so in the problem, if they hadn't given you the function, they would have said that the car was purchased for $24,000 and that the car's value decreases 20% a year. So that way, when you went to write your equation, you would have changed the 20% to the 0.2. And then remember, it's always 1 minus r, so you'd have done 1 minus 0.2, and that's how they got the 0.8. So really, it's having you think about it backwards. All right, next they say, graph the function on a reasonable domain. What do the y-intercept and the asymptote represent? Well, again, I could actually sketch this picture without my graphing calculator. In just a second, I'm going to go to the graphing calculator to answer the last question, and so we'll do this there. Now, reasonable domain, though, I can't have negative values, both for time and money. So I could start both my x and y at 0. Now, we know that the car was purchased for $24,000. So, but we use 24 because it's in thousands. So I'd probably go up to like 30 so that I know I could see that y-intercept at 24. We know it's decay and it hasn't been shifted, so it should look something like this. Now, in terms of my biggest x value, again, x, we're talking about time. I want to think about, like, how long could a car survive? Good cars last about 20 years, so I would maybe go up to 30 there as well, just so that I get an accurate picture. But again, most cars don't last for 30 years. You could have gone to 20 or whatever. Okay, now this question says, when will the value of the car be about $5,000? Well, that's actually saying, when does 5,000 equal 24 times 0.8 to the x? The problem is we do not yet have an algebraic way to solve for an exponent. We'll learn it this chapter, but right now we don't know how to solve for an exponent algebraically. So we're going to have to use our graph. In order to do that, now, oops, I shouldn't put 5,000 here. Let's correct that. It would just be 5, right? Because 24,000 is 24, so 5. We have to put it in thousands. So in order to figure out what this is, remember, if we want to solve graphically, this is just a great skill to have on hand for pretty much anything. You could graph 24 times 0.8 to the x, we did, and then separately, we're going to, or not separately, but in the same grid, under y2, we'll graph 5. We'll find this point of intersection. Its y value is going to be 5, but whatever that x value is, that's the value of the car, or that's when the value of the car will be 5,000. Okay, so let me switch over to my graphing calculator so that we can take a look at it. So in my graphing calculator, and again, I can't encourage you guys enough to get the TI-84, and for now, be using the online version that your teachers provided for you rather than Desmos, because in your future, you're going to have to know how to use this tool. Okay, so y equals And I'm first going to graph the 24 times, and we had 0.8 to the x. Caret key gets me to the exponent, and then I have to use this giant x button. Okay, so that's my first function, but remember we said that we had to graph y equals 5, so we can find the point of intersection. Now we also talked on the previous screen about changing our window to a realistic domain. We said that our minimums can be 0, and again, x is number of years. We said a car is probably not going to last more than 30 years, so I go windows, x is from 0 to 30. My y minimum, again, I'm not going to have $0. I mean negative dollars, but I could have 0, and then my maximum, again, we want to go up to 30,000. Once we have all that typed in, we hit the graph button, and we can see a nice, neat picture. Now, as a reminder, how we find this point of intersection. This calc, the blue calc above trace, is where you always want to go and you want to calculate things on your graph. So we go blue button, second, calc, and then we can see that the intersection is number 5. You can either scroll down to number 5, or you could have just hit the number 5 on your keypad. Now, it says first curve. Yes, this cursor is on the first curve, so I hit enter because I'm saying yes. Notice the cursor jumped to the red curve, and it's saying, is that the second curve you want it to find? Yes. And do you want it to guess? Yes. It's not actually guessing. I wish that said calculate. But now we can see that it tells me the point of intersection is 7.03. Okay, so this will intersect about 7 years after. So after about 7 years, the value of the car will be about $5,000. Okay, one quick thing while I'm still here in my graphing calculator, we've also been typing things in exponentially. So for example, the last one we typed in, or the very first one, was 4.6. I just want to make sure you know how to type these in. So when we did 4.6 times 1.013, you need to make sure you close your parenthesis, and then anytime you have an exponent bigger than 2, you do caret key, and then that number. So we did to the 30th power. Okay, so that's where I was doing that. So you do have to be able to type in exponentials. So again, when we typed this in, we got this to be about 7 point something. So after 7 years. Okay, so here we go. Interpret an exponential function. You try it on your own. So pause the video and see what you get. Hopefully you saw that the population was increasing because B is 1.05, and that's greater than 1. Okay? What is the, in what year will the number of hawks reach 280? Sorry about that. So this is my total number. So we had a situation where you had 280 equals 220 times 1.05 to the x. Again, hopefully you used your graphing calculator. You could have put this under y2 or y1, this under the other. When I graphed this, I had this situation, and I got 4.94, 280. Now, when I thought about my window, again, I started at 0 in both directions because I can't have negative numbers. Since my starting value of hawks was 220 and I wanted to know when it was 280, I changed my y from 0 to 300, and I left my x's at 0 to 10. I really had no idea how many years it would take, but I started just by leaving that as the default, the 10. And as you can see, since it took 4.94 years, it was plenty of room to see it. Now here's where you have to be careful though. So we got 4.94 years, which means in the 4th year, it reached 220 hawks. But the problem is it wants to know in what year. So this is a situation where you have to understand that it started in 2016. So for my final answer, I do 2016 plus 4. So in the year 2020 would have been your final answer. Okay, so you do have to make sure you can convert it to that situation. All right, last but not least, we have to be able to compare two exponential functions. It says a museum purchased a painting and a sculpture in the same year. Their changing values are modeled as shown. Find the average rate of change of the value of each artwork over the 5-year period. I hope that you remember what average rate of change is. When you've heard average rate of change, hopefully you've thought about slope. Okay, it's the change between 2 points on a line. When we did slope, we know that it's y2 minus y1 over x2 minus x1. And you might say, well, Ms. Sliminski, but we're not talking about lines right now. We're talking about exponentials. However, if they ask you to find the average rate of change between 2 points, even on an exponential curve, you're actually finding the rate of change, which means you're finding the slope between those points. I'm going to start with the graph on the right-hand side. They're telling me that this point is 0.40 and this is the point 564.4. And the reason I want to start with the graph is because really what you're doing is you're saying, if I drew a straight line between those 2 points, what is the slope of that line? And so that is why, yes, to find that average rate of change over 5 years. In this one, they give me, so we'll call this one x1, y1, x2, y2. I would take y2, which is 64.4, minus y1, which is 40, over 5 minus 0. Okay, so I get 24.4 over 5, and when I type that in, I get 4.88. Now remember, these are in values in thousands. So 4.88 is actually $4,880. That's the average rate of change over a 5-year span for the painting. Now the sculpture, good or bad, they give me in function notation, which means I actually have to find the value of the painting at time 0. Type that into my calculator and I get 50. That means the first starting point is 0.50. So you actually have to calculate the points that they gave you in the other. And then I want to find the value 5 years later. So I would do f of 5. 50 times 1.075 to the 5th. When I type that in, I got 71.78, which means my second point is 5, 71.78. So if they give you a function and ask average rate of change, you have to plug in the 2 endpoints of the values. So x is 0, x is 5. That's the 5-year span. And now we would do y2 minus y1. So I take the 71.78 minus 50 on top. Those are the difference of my y's, over 5 minus 0, the difference of my x's on the bottom. This one gives me 21.78 over 5, which gave me 4.356. Again, I convert that to thousands, which means I multiply by 1,000. I get $4,356. And again, the question was, which one is increasing more quickly? Which means the bigger rate of change. Okay, so that means the bigger average rate of change. Okay, and so then I would look at this. This number is bigger, so it's the painting, because its rate of change is bigger over that 5-year span. All right, last but not least, I want you to try one of these on your own. Go ahead and pause the video and just answer the question. Again, the problem is the same, but we're asking a different question. Will the value of the painting ever surpass the value of the sculpture according to these models? And explain. Hopefully, as you were thinking about this, you were like, okay, so even though the value starts higher for the sculpture, right? So this one started at $50, this one started at $40. Because the painting value is increasing at a higher rate, it had the higher rate of change, yes, eventually the painting will be worth more. Okay, so that was really just more of a thinking one than a doing. All right, here's a summary of what we've been looking at in this entire section. You can pause it if you want to get any additional notes, but otherwise you can move ahead and work on your 6-1 day 2 Pearson practice.